Good morning. So let us continue with tutorial number 6, Applied Thermodynamics course. Problem number 12. Liquid water at 15 degrees is heated in an insulated chamber by mixing it with saturated steam. Liquid water enters the chamber at the steam pressure at a rate of 4.6 kg per second and saturated steam enters at a rate of 0.23 kg per second. The mixture leaves the mixing chamber as a liquid at 45 degrees. So, it's a mixing chamber. So, it's an insulated one. So, liquid water at 15 degrees. This is saturated steam. So, here liquid at 45 degrees comes out. So, this is the configuration which we are going to. The flow rates are given. Liquid water enters at steam pressure, the same pressure, okay, the rate of 4.6 kg per second, and the steam enters at the rate of 0.23 kg per second. Okay. Determine the temperature of the saturated steam. Here, the Exergy destruction during this mixing process and the second law efficiency. So, this is the problem. The liquid water temperature at inlet, you can say 15 degrees centigrade, and so this says stream 1 and this is say stream 2 and this is the mixture coming out is stream 3. These the streams are numbered 1, 2, 3 accordingly. So, this will be 4.6 kg per second and this is the steam's flow rate is 0.23 kg per second and the T3 is given as 45 degrees centigrade and m dot 3 will be equal to m dot 1 plus m dot 2. So, steady flow, steady state steady flow. So, we can see this will be equal to 4.83 kg per second. So, now state 1 is subcooled liquid. So, from 15 degrees saturation table entry, we get H1 equal to 62.99 kilojoule per kg and S1, the entropy is 0.2245 kilojoule per kg Kelvin. So, from the steam table you can get this. Similarly, I will get the state 3 properties. Again, it is liquid at 45 degrees. So, from 45 degrees saturation table entry, HF and SF are taken. Okay. So, H3 will be equal to 188.4 kilojoule per kg and S3 will be equal to 0.6386 kilojoule per kg Kelvin. So, you can take the tables and get this value, but we are not certain about H2. Only thing what is known is it is a saturated vapor. So, H2 is Hg at steam pressure. Okay. So, what is that pressure? So, we have to determine this by using first law. Solution continued. you get by first law q dot minus wx dot, both are 0. So equal to 0 equal to m dot 3h3 minus m dot 1 h1 minus m dot 2 h2. So here potential energy and kinetic energy changes are neglected. So no work and heat interaction. So this is the thing. So we can substitute here 0 equal to 4.83 m3 into h3 is 188.4 minus m1 is 4.6 into h3 is h1 is 62.99 minus m dot 2 is 0.23 into h2. h2 is unknown. From this I find h2 as 2696.4 kilojoule per kg. Okay, now we know that this should be Hg at P2 or the steam pressure. Okay, now how will you get this? You go to the tables, basically 2696 is the value. So if you take this table, so here you see that you concentrate on the Hg values here. So 2696 basically here 2691 is there at 110. So maybe we can take the closest value, or we can say that that temperature will be in between 110 where the Hg is 2691 and 120 which is 2706. So we can interpolate between these two and get the value. So closest value is 110. So just by looking into tables I can get the value of the Hg. So you can also do this from the table, pressure based table. Here, okay, here also you can do. So 2694 is there. You can see this 1.5 bar 2694, which is also very close. So, but temperature you can see 111.4. So you can take any value. So the pressure is around 1.5 bar and temperature is around 111 degrees. So go back to solution. From saturation tables, P2 is found as 1.5 bar and T2 is 111 degrees centigrade. Okay, so that's what we get. So again you can interpolate and get the S2 as 7.20 kilojoule per kg Kelvin. Sorry, S3, S2. Okay, so now you have got the values. Now apply the entropy balance. S gen equal to delta S gen minus q dot by T naught. So now this is written as m dot 3 S3 minus m dot 2 S2 minus m dot 1 S1. So this is equal to 4.83 into 0.6386 minus 0.23 into 7.2 minus 4.6 into 0.2245. So that comes out as 0.3957 kilowatt per Kelvin. The irreversibility I is nothing but the entropy, the exergy destroyed, that is T naught into S gen. That here the T naught is given as 15 degrees or 288 Kelvin. So this will be 288 into 0.3957, which is equal to 113.96 kilowatts. That is the irreversibility. Now, second law efficiency is asked. Second law efficiency is calculated in many ways, as I told you. For work producing device, it is the actual work produced divided by the reversible work which can be produced. For the work absorbing, it is the reversible work input divided by the actual work input to the work absorbing device. But here there is no work involved, so we can find the second law efficiency as ratio of the outgoing exergy divided by incoming exergy. Okay, so this is one way to do. So outgoing exergy, I will calculate. Outgoing exergy can be calculated as what is going out, m dot 3 into H3 minus H, the dead states enthalpy, minus T naught into S3 minus S naught. So that is the exergy divided by the incoming. Incoming exergy will be equal to the sum of the two streams. No? So here m dot 1 into H 1 minus H naught minus T naught into S1 minus S naught plus m dot 2 times H2 minus H naught minus T naught into S2 minus S naught. Okay. So now we can see that the state 1 is same as the ambient state, because you can see that the temperature of the incoming steam stream is 15 degrees centigrade, which is also the ambient temperature. Okay. So H1, H0, S1, S0 are the same. So this goes out. We can find the value of this as 143.625, and for this we can find the value as 29.65 kilowatts here also. So that means the second law efficiency will be equal to 29.65 divided by 143.625, that will be around 20.64 percentage. So this is the, so due to the mixing, you can see the irreversibility is very high and the second law efficiency is very low. So this is about this problem where two streams are mixed and the mixture goes out at the required state. So here the water is heated. Basically this is used in the thermal power plants to reduce the sensible heat added to the water by adding some mix, the steam which is coming out from the turbine partially withdrawn and mixed with the condenser outlet water, so that you get a higher temperature reaching the boiler. 13th problem, a stream of hot gas mixture from a combustion chamber steadily flowing at a rate of 12.5 kg per second at 300 degrees is cooled in an insulated heat exchanger using an air stream flowing at a rate of 11.5 kg per second with an inlet temperature of 40 degrees. The exit temperature of the air is 160 degrees. Let us draw this. Something like this we can say. So this is the air, 160 degrees and 40 degrees. The air comes out. So this is the air stream, and this is hot gas mixture. So the flow rate of hot gas mixture is 12.5 kg per second. For the air, this is 11.5 kg per second. and the inlet and outlet temperatures of are 40 and 160 is given. Here the inlet temperature is 300 degrees centigrade. So that is what is given. Flow rate is given for the both streams, and here the outlet temperature. So T gas 2, that we have to determine. C of gases, Cp for the gas, Cp for the hot gas mixture is 1.1 kilojoule per kg Kelvin, and Cp for air is given as 1.005 kilojoule per kg Kelvin, and ambient temperature T naught is 300 Kelvin. So there is no pressure loss. So for example, the constant pressure, the hot gas goes through constant pressure, almost constant pressure. Similarly, air stream also goes with constant pressure. So there is no pressure loss. Calculate the incoming and outgoing availability or exergy and of the hot gas mixture and the irreversibility during the process. So that is the question asked. So solution. First law. So here the insulated heat exchanger is given. So the heat exchanger is insulated. So first law, Q dot 0. Similarly, there is no work interaction. So that is also 0. So that will be equal to, again you can say the for the gas, if the mass flow rate is m dot g, you can say H outgoing enthalpy value, specific enthalpy, and the Hg1 plus m dot A into H A2 minus HA1. So this is the first law. I can write 0 equal to, for the gases is 12.5 into C value is Cp value is 101.1 into Tg2 minus, it is coming in 300 degrees centigrade. So I can put that value 300 plus 11.5 into 1.005, that is m dot for air and Cp air into outgoing temperature is 160 minus incoming temperature is 40. So this is the first law expression from which I find the value of the outgoing temperature of the hot gas mixture as 199.13 degrees centigrade, almost 200 degrees centigrade. So 100 degree is spent out. So this is like a air preheater, where air is heated and sent to the furnace. From the furnace, hot gas comes out at 300 degrees and goes out at 200 degrees. So this is the, so now we got the states fixed. So now we go to the incoming exergy calculation and availability. Incoming exergy, that is m for the gas, for hot gas mixture. So we can say m dot g into H1 minus H naught minus T naught times S1 minus S naught. So now this basically can be written as 12.5 into this H1 minus H1 can be written as 1.1 Cp into T1, that is 4573, that is 300 plus 273 minus H naught. Ambient temperature is 300 Kelvin, so that I write as 300. So this is this term minus 300 into, so now S1 minus S naught can be written as Cp into natural logarithm of 573 by 300. So there is no pressure. So we can assume pressure is not changing, and this, the pressure term will not have any issue influence here. So this is Cp ln Tg2 by Tg1, Cpg. So that is what this term is. So when you substitute this, I get the value for incoming Exergy as 1084.45 kilowatts. Okay, so pressure change is 0. So minus R ln P2 by P1 will be equal to 0. So this is incoming Exergy. Now outgoing Exergy, which is asked, is m dot g into h2 minus h naught minus t naught times s2 minus s naught, which is equal to 12.5 times 1.1 into 272.13, that is 199.13 minus this is 300 minus 300 times 1.1 into ln of, so this is 472. 199.13 plus 273, 472. This is again 472.13 divided by 300. So that is the value here. So this comes out to be 496.22 kilowatts. So that is the, what is asked is incoming Exergy and outgoing Exergy for the hot gas mixture that we have found. Now entropy balance. So you can see that due to the heat transfer, the Exergy has decreased. Incoming stream has higher Exergy and outgoing stream has lower Exergy, and this has actually gone out as heat transfer to the air stream. Now entropy balance for the control volume. So the entropy balance for the control volume, where I can write S gen Cv equal to m dot g into Sg2 minus Sg1 plus m dot a into Sa2 minus Sa1. There is no Q and all. So the only S then C will be equal to, this is actually what? Delta S dot. So minus Q dot by T naught, that will be 0. So this will be this. So now how will I do this? Again pressure ratio is same. So the incoming and outgoing pressures remain the same. So I can say this is m dot g into Cpg into ln of Tg2 divided by Tg1 plus m dot a Cpa into ln of Ta2 divided by Ta1. So we know all the values. Substitute and get the value of the entropy generated, that is 1.088 kilowatt per Kelvin. Now irreversibility is nothing but T naught into S gen, which is equal to 300 into 1.088, which is equal to 326.4 kilowatts. So this is another problem where the heat from the hot gas is transferred to the air to preheat it, and that preheated air is supplied to the furnace. 14th problem, a chilling unit cools a commodity at a rate of 1000 kg per hour. The commodity enters the chilling unit at ambient state of 1 bar 300 Kelvin. The commodity may be anything, like any food commodity or anything, and exits at the same pressure, but it is cooled from 300 Kelvin to minus 20 degrees centigrade. The freezing point, specific heats below and above the freezing point of the commodity, or freezing point is minus 2.2 degrees centigrade. The specific heat below the freezing point is 1.7, above the freezing point is 3.2 kilojoule per kg Kelvin. The latent heat of fusion, so it has to freeze. Okay, that for that you have to remove 235 kilojoule per kg. So determine the rate of heat interaction and the rate of Exergy change during the chilling process. Solution. So it's a phase change problem. Okay, so now first law, q dot minus w x dot, so that is 0 equal to, now I can say m dot, that is 1000 kg per hour, into, first I have to cool it from 300 Kelvin, that is 27 degrees centigrade, to the freezing point minus 2.2. So, that is now the Cp has to be above the freezing point. So, you select the Cp above the freezing point. So, 3.2 into the final temperature is minus 2.2, the freezing point itself. So, what is that? 270.8. So, this corresponds to 2.2 minus 2.2 degree centigrade minus the initial temperature is 300 Kelvin. Okay, now I have to remove the latent heat also. So, that also you put minus 235. Since I am removing, I have to put a negative sign here, plus 1.7. Now, it has reached the freezing point. Now, further cooling will decrease temperature after the freezing occurs when you remove the latent heat of fusion. Now, further cooling will reduce the temperature from 2.2 minus 2.2 degrees centigrade to the final temperature of minus 20. Okay. But when you remove the latent heat of fusion, the temperature remains at the freezing point, which is minus 2.2 degrees centigrade. So, now final temperature is 253, that is minus 20 degrees centigrade minus 270.8. This is minus 2.2 degrees centigrade. Okay. So, this is the conservation. So, from that I can find Q, the rate of heat interaction. So, Q dot, now this is what? This is 1000 kg per hour, which is equal to 1000 by 3600 kg per second. When I substitute it, I will get the heat transfer as minus 99.64 kilowatts. The heat is removed, so negative sign comes. Almost 100 kilowatts is removed in order to cool the commodity at a rate of 1000 kg per hour from 300 Kelvin to minus 20 degrees. So, now second one is rate of Exergy change. So, here we have to find the rate of Exergy change, that is this final state Exergy minus initial state Exergy, the rate, which is written as m dot into h2 minus h1 minus t naught times s2 minus s1. Okay, now let us find one by one. H2 minus h1 will be equal to, here 3.2 into 270, same thing will come, 270.8 minus 300, that is because of the Cp value being different for when the temperature is above the freezing point or below the freezing point, we have to do this. Again, we have to consider this latent heat also. The total enthalpy change will also include the latent heat, which is this, plus 1.7 times 253 minus 270.8. So, this will be equal to minus 358.7 kilojoule per kg. Now, S2 minus S1. S2 minus S1 we can write as 3.2 into ln of 270.8 divided by 300 is C ln T2 by T1, that is the formula. Okay, minus, when the latent heat is removed, temperature remains constant at minus 2.2 degrees, that is 235 kilojoule per kg is removed. Now, the temperature at this point is, this is minus 2.2 degrees centigrade plus 1.7 into ln of 253 divided by 270.8. So, this will be equal to minus 1.311 kilojoule per kg Kelvin. Okay, please understand that in the phase change, when there is a complete phase transformation to a frozen product from initially which can be liquid or any other thing, it is completely now frozen. So, for that you have to include this term, that is the latent heat, the entropy change due to the supply of latent heat at constant temperature. Okay, now we got these values. Now we have to find the rate of Exergy change. Rate of Exergy change equal to the flow rate, that is 1000 kg per hour divided by 3600 into minus 358.7, that is H2 minus H1, minus T naught is 300 into minus 1.311. So, that will be equal to 9.608 kilowatts. So, that you can see that Exergy change of Exergy is this. Exergy will be always positive. So, this is about this problem where a phase change occurs and we are using different CPs when the commodity is below the freezing point or above the freezing point, and we should not forget to include the latent heat in the enthalpy change calculation and latent heat by the freezing point temperature in the entropy change calculation.